because how do you find a contraction of this loop? But the sort of issue that one may run into is that maybe the contraction exists, but it has to go through loops of length, longer in light years than the heat death of the universe. And so at that point, does that really count as a contraction or not? In fact, it's not, your metric on the universe doesn't need to be that big or complicated in order for something like this to happen. And so, right, just looking at this physical or maybe not so physical process, you might come up with a definition, right? So I'm given a metric space Y. And first of all, if I just have a loop, I can talk about its filling length. This is, you look at all the possible ways of null homotopping this loop. So I guess it has to be a null homotopic loop. And you minimize over all these null homotopies. The size of the largest loop you have to go through. And now that we've defined it for a single loop, we can also define the filling length function. Of Y to be, right, you plug in some length and you maximize this over all loops of that length. And yeah, so here's a little sketch of what's going on here. You start with some loop, and maybe you have to go through much bigger loops to contract it. And so the length, right, this length as a function of this length is what we're looking at. And it's not hard to see that if Y is, say, a compact manifold or some other nice space, then at least, up to some suitable equivalence relation, this only depends on the fundamental group. So asymptotically, this is a property of pi 1 of Y, and so really this is some kind of invariant that naturally belongs to geometric group theory. And we can look at some examples. So it's a theorem of Riley that for nilpotent groups, this is linear. And
so this is what Y is a manifold.
yeah, so, or right, some probably it's enough to be Lipschitz homotopy equivalent to a manifold. And Lipschitz homotopy equivalence is really the relation that I'm mostly going to be caring about. But you might ask, can this get really big? And indeed it can. This is an observation that's maybe due to Novikov or maybe Gromov, I don't know, some linear combination of the two. Suppose pi1 of y has an undecidable word problem. So there's no algorithm to tell whether a word or a loop is trivial or not, whether it's contractible or not, and it's a theorem of Novikov that such groups exist. Then, well, if you had some kind of bound on how big contractions could be, then you could figure out whether the loop is contractible by going through every possible contraction that obeys that bound. And so that means that this filling length function, like many other functions related to the geometry of this group, has to grow faster than any computable function. So faster than a tower of exponentials, for example, and so on. Any function that you could really write down, it grows faster than that. It's also the case that there's no algorithmic way to distinguish y with this property from spheres. And so therefore, and this observation maybe is due to Nabotovsky, you can find metrics on the sphere where you can still contract all the loops, and this fact tells you that there's a linear way of contracting all loops, but the constant, depending on the metric, it might depend on the metric in an extremely wild way. And this is, this goes back to my comment about the fact that you don't need a huge metric in order to have huge contractions. Okay, so, but let me get to what the title of my talk was about. We can take another perspective on this same sort of problem, and we can think of length as a height function on the space of curves. So the loop space of y, and then maybe it looks something like this. It has multiple components, and then this filling length function is, it's sort of telling you if you happen to be at a local minimum, how far up do you have to go in order to fall back down to the global minimum? In other words, as you take sublevel sets of this landscape of the length functional, you see spurious components appear, and then at some point they disappear again. And so maybe the more general question is, how long as you fill your space with water, does it take for spurious components to disappear? Okay, and then the idea, which again is due to Gromov, maybe in the 90s, is that you can extend this sort of line of questioning in two different directions. First of all, we can consider, right, so far we've been considering some target space Y, and our domain is a circle, but we can consider other domains. Right, and then I have to tell you what the right height function is. And you know, you could choose various things. You could choose Dirichlet energy, for example, and that would produce a different theory. For me, this is always going to be the Lipschitz constant. And this is, you know, in part because I have the tools to analyze the Lipschitz constant, and in part maybe because I'm really a discrete geometer at heart, and the Lipschitz constant tells you the scale at which you need to subdivide in order to sort of combinatorialize your map up to a small deformation. And for basically technical reasons, I'm actually going to take the log of the Lipschitz function, the Lipschitz constant. So it'll be clear why in a little bit. And right, the second extension that you can imagine is, instead of, right, here we're just considering components of these sublevel sets, but we can also consider the higher dimensional topology of the sublevel sets. Right, so maybe somewhere over here I have a one cycle, and then it actually has a contraction, and then you would ask, you know, how high do you need to go in order to find that contraction? So this is, you know, a circle's worth of loops. Okay. So, and there's a standard formalism that's used for studying things like this. which is called persistent homology. So let me give a very brief crash course in what that is. So someone gives you a space and a filtration of that space, right? So let me call the space Z, and it's the union of some ZTs where, right, this is an ascending set as you go through this continuous time variable. I guess in our case, the time variable is this log of the, well, I guess the log can be negative, but whatever. Let's not worry about that. The persistent homology is just the homology of all this data. So PHN of Z, this is, you take all the HN of ZTs and you know, all the maps induced by the inclusions. Right, and so far we haven't said anything. But here's a way to make sense of all this data. This is due to Zomerodian and Carlson. First of all, we have to assume that we're using field coefficients. If we're not, then things are more complicated. There's a way of decomposing or finding a basis, finding consistent bases for the various HN of ZTs, where what I mean by consistent is that, right, when you go from HN ZT to HN ZS, all the basis elements, they either go to basis elements here or they disappear, right? And in fact, distinct basis elements, right? So the way this is usually pictured is that these basis elements are born at some time, and then they continue through time, and then they die at a different time. So let me give a simple example. Just for pH 0, let's say I have this picture, right? Then I have one component that is born over here, and then I have another component that's born over here, and over here they merge, right? So merging is something that you're not allowed to do here. But if you take the difference between these two components and make that your basis element, then that difference is born here, and it goes to 0 over here, it dies. So the persistent homology, the pH 0 of this object is going to look like this. There's one bar that goes all the way up, So this is an infinite bar. And there's one bar that's born here and then dies over here. So that's a finite bar. Yeah, and in fact, right, so the way this basis is actually chosen is if you just have finitely many points where the topology is changes, or even if it's a well-ordered set of points where the topology changes, then you can view the whole thing as a module over a polynomial algebra and you use the decomposition of those. And so, yeah, you sort of don't need to do anything fancy. And in this case, we have, we can have things appearing and disappearing at a non-discrete set of times, and that's okay. You can just sort of take a limit, right, as you take finer and finer times.
So you need this field, because FOZ should be...
Yes, you need field coefficients in order for this to be well-defined, yes. Okay, so now I can give some results. From our joint work. So I'm going to start with a sort of oddball that doesn't fit into the rest of the framework. So if you have a non-positively curved manifold as your target, then for any domain this persistent homology of the Lipschitz functional has no finite bars whatsoever. What actually happens here is, every time a connected component is born, it has all its topology already there, and then every sublevel set has the exact same topology. And this is actually not hard to prove. You use the convexity of non-positively curved spaces, and then you do a small exercise in algebraic topology, and then you're done. But sort of why I wanted to throw this out here is that this property of not having finite bars, this is not a topological property. This really depends on the geometry. Right, because I could add a little bump to say I had a non-positively curved surface and I added a bump to it, and suddenly I have infinitely many finite bars, right? One for each number of times you go around this curve, at least.
Is there any assumption on x's or y?
No assumption on it. Yeah, no, I think x is any metric space. Yeah.
And do you take like rational homotopy groups rather than homology with field coefficients?
Sorry?
Can you take rational homotopy groups rather than...
Yeah, you could. Yeah, you could.
That could be discrete, so it would be really any, so it would just be metric space or really
Yeah, I think so. I mean, yeah, I haven't thought quite about how general it is, but it really only depends on, oh no, I guess, okay, yeah, we use the fact that x has a fundamental group in the argument, so maybe x should be something good enough to have a reasonable fundamental group. Okay, so let's fix this issue. So suppose that X is Lipschitz homotopy equivalent to X prime, and Y is Lipschitz homotopy equivalent to Y prime. And here you can think, right, for example, they're homotopy equivalent Riemannian manifolds because, you know, any continuous map between compact Riemannian manifolds between such objects, you can make Lipschitz. So the Lipschitz bit doesn't matter. Then the persistent homologies of these two pairs of maps between these two pairs of spaces have what's called finite interleaving distance. So what this means equivalently is that, you know, for one you have one set of bars, and for the other one you have a different set of bars. Maybe they're a little bit off, and maybe there are some extra tiny bars, but you can match them up so that all these distances are less than some finite delta, and then you can throw away the guys that are less than delta long. So in particular,
What's the name of the distance?
interleaving distance. So the technical thing there is that you're going from hn of zt to hn of z prime t plus delta, and then back to hn of z of t plus 2 delta. So yeah, they sort of interleave between themselves, each other. And so, for example, right, no finite bars is not a topological property, but if you take the property all finite bars are of bounded length, then that's I guess Lipschitz homotopy invariant with respect to x and y. So this is sort of the nicest thing that you could hope for that's a topological property. And so we have some situations in which that does hold. So if y is simply connected, then all finite bars in the loop space, in the persistent homology of the loop space, or you can take the free loop space, so unbased loops are of length at most, well, the constant actually depends on n, so I guess it's not quite the best you can hope for, but it's pretty close. And Yeah, I guess I should reiterate, what does it mean for the bars to be of bounded length? That means that in order to kill your spurious cycles, you need to increase the Lipschitz constant by at most a multiplicative constant, right? Because you're adding a constant to the log. Sorry?
You don't need a metric on the loop space?
No, all I need is a height function. And my height function is length.
Oh, you're defining the subset. So
Yeah. And then the other situation in which we can get this property is if, let's say, X has locally bounded geometry. So when I write down theorems like this, I usually say X is a simplicial complex where the simplices have a standard metric on them, but you can also use other forms of locally bounded geometry. It doesn't really matter. And Y is a nilpotent space with positive weights. So nilpotent space, you can think of nil manifolds or simply connected spaces. And the actual definition is slightly more general, but the other ones that are not in those two classes don't seem to show up very often. And with positive weights is this kind of weird technical condition that basically says that the space has lots of self-maps of different degrees. So, for example, if you're looking at a nil manifold, then this is saying that pi1 of y is graded. And if you're looking at a simply connected space, then most of the simply connected spaces you can imagine do have positive weights. And of course, if you somehow take a random simply connected space, then almost none of them do, but they're hard to construct. Right, so in this case, also all finite bars, sorry, but not of the whole mapping space, but just the component of the constant maps are bounded. And so at this point, you might ask, okay, when is it not? Are these just feeble attempts to prove something that's true much more generally? And at least in some cases, we know that this isn't true. So if you remove this component of constant maps, then there's a sequence of maps between the following two spaces, S2 cross S2 cross S3 wedge S3 to S3 wedge S3, right? So these are in many ways very nice from the point of view of rational homotopy theory. they're not very complicated, where, you know, their Lipschitz constants go to infinity, and they're homotopic, but any homotopy goes through maps whose Lipschitz constant is at least on the order of L to the 4/3. So if we had bounded finite bars, then this would be linear in L, and in this case it isn't. All right. So it looks like I have about 7 minutes or 8 minutes to say something about the proofs. And really, I wanted to talk about a little bit about the proof of theorem C. The reason is that it's a very simple application of of a tool that I've been using for the past 6 or 7 years repeatedly, you know, I'd like that tool to also be useful to other people. So the idea is that, okay, so in this case, we're trying to construct a Lipschitz map with some properties, right? So in this case, what we have is some kind of, you know, here's my my space and space of maps, I guess loop space, right? And then I have some kind of cycle in here, and I know I can, and this is living in length at most L, right? And then I know I can kill it with something that might go.
The functional is length here or the Lipschitz?
Length, but it really doesn't matter, right? Like you can reparameterize, you can just take the subspace where all your curves are reparameterized by arc length, and that's obviously a deformation retraction. So for loop spaces, I'm going to be vague about whether I'm talking about length or Lipschitz constant. Right, so, and I can think of this cycle and its filling as a map, right? This is some map from some pseudo-manifold with boundary. Ugh. To the loop space, and right, I can, so you're mapping from this object to loops. You might as well think of this as mapping from the object cross S1 to Y, right? So let me say I have this map zeta from a map like this, right? And so now, and I might as well, you know, right, a priori, this is just some cycle. I don't know how I'm varying the loops, but I can always deform it a little bit to make it Lipschitz. So we might as well assume that this is Lipschitz, but with huge constant. So now, I'm going to take this this map and apply Sullivan's model of rational homotopy theory. So what this means is instead of taking the map, I take its pullback on differential forms, right? And okay, Lipschitz, why can I pull back differential forms? Let's say they're flat forms, whatever, I don't really care. And then there's a way of selecting some finite set of these forms that give me most of the topological information about my map. And so this is living in some space of homomorphisms from this object my to forms on this guy. And a theorem of mine, which was published in 2019, which I called the shadowing principle, says in a sense that I don't have time to describe that somehow the images of genuine maps are reasonably dense in here. Right, so where by images I mean I'm going from zeta to this composition with this fixed map and then the pullback. And so what this allows us to do in this situation is, okay, so this reasonably dense depends on the metric on the domain. And so what we can do is make the metric on Z, let me call it really big G because it's really big. And you know, plugging in this homomorphism into the theorem, right? So since this is a little bit pointless because I haven't actually explained what the theorem says, but right, with respect to this huge metric on Z, the operator norms of these forms are not too big, right? I can make them at most little l if I make big G big enough. And that's just because, these forms, they are at least two forms because the space is simply connected, and every at least two vector has a component, right, in Z cross S1 has a component in the Z direction. right? And now this tells me that there's another map, let's say zeta prime from z cross S1 to y, such that, you know, on the boundary of z cross S1, it's really the original zeta, and then, and everywhere it's some CL Lipschitz with respect to the metric huge G plus the usual metric on S1. So, and that proves the theorem, right? We traded the height of this cycle for basically its width. Thank you very much.